well from your papers.
Oh, hi. Hello. I've never met you too, but I'm looking forward to your talk.
Thank you. Thanks for coming.
Yeah, yeah, of course.
Yeah,
Yeah,
yeah. I enjoy a lot of reading your papers. I always wanted to talk to you. But
thanks. Thank
anyway,
you.
yeah, yeah. Last week I actually chat with Hota.
Oh, I see. Oh,
Yeah.
wait. Oh, where Hota was visiting you, or how did?
No. I gave a talk at MIT, and he attended it.
Oh,
So
I see.
we ended up chatting.
Oh,
Uh,
nice, nice,
and
nice.
he asked the cool questions, and yeah, it was very fruitful conversation.
I see.
Yeah. Are you guys keeping track of word? Are you recording by now? By the way, Juven? Okay. Yes. Okay. Then let's be neutral.
How is your axion string work going?
Yeah,
Are we going to be able to see it soon?
Yeah, we are really pushing. We are really pushing. It's just that I got caught by by the grant proposal. So
Well, of course.
I have to secure next 3 years or so. So I have to do that. But yeah, we are
Also
pushing.
important.
Yeah, all the physics I think are sorted out completely, and so basically.
Good, good. No, that'll be very exciting to see.
Yeah. Thanks.
I guess we can really start. People might join in late, but that's fine. So, okay. Welcome everyone to Harvard CMSA Quantum Math seminar. 모두 환영합니다. We are glad to have Sungwoo home from Korea Advanced Institute of Science and Technology. He recently moved from U Chicago to KAIST. And he'll be speaking about his exciting recent work jointly with Clay, Seth, and Kantaro on this neutrino mass from generalized symmetry breaking. Let me remind the audience, please feel free to interact with Sungwoo and ask questions during his seminar. So let's welcome Sungwoo. Yeah, please take over.
Yeah, thank you, Juven. Thanks for inviting me and providing me a chance to speak here. It's very nice to see people in US. I'm already missing being in US and doing physics in US and talking to people in US. So I'm very happy that I have this chance, even virtually. So yeah, so today I would like to talk about my recent work with excellent collaborators, as Juven already talked about. Let me do that again. With Clay Cordova and Seth Curran at University of Chicago and Kantaro Mori at University of Tokyo. So it was a lot of fun, and hopefully I can convey the joy we had. But please, again, interrupt any moment and ask questions. I'll do my best. Right. So yeah, generalized global symmetries, and I'm not quite sure the composition of audience here, but it's such an exciting word, a big word, at least to me. And here I'm coming from more particle physicist perspective, or actually particle physicist phenomenologist. But so let me start by saying that most symmetries we see and use in particle physics act on local operators, especially particles, right? So given, for example, local operator that represents excitation of, or who can excite the particle excitations, and if we have some symmetry under which this field operator, local operator changes, we know that we can check whether given theory is invariant under such global symmetry or not. For example, if we had an electron, we can surround it by three-dimensional, defect or manifold, and we can check whether it has a unit charge or different charge under such a symmetry. Now, recently, by recently, I mean really recently, although there has been a lot of development already from a long time ago, but the concept of symmetry has gone through really explosive generalizations, and there are many directions. And all those beautiful generalizations are adopted by now as a generalized global symmetry as a whole. So to my mind, the most used and most worked example is higher form symmetries. Here, as a bottom-up approach or perspective, we just realized that there are various extended objects appearing in broad class of field theories, right? So for example, we start with a point object like a local operator or particles, and any symmetry that can act on this local operator, we call it a zero form symmetry, because here the charged object is a zero-dimensional object. Now we can easily think about line operators. For example, if we had word like a massive particle, which is very, very stable, and for example, it is electrically charged, therefore it will look like Wilson loop or Wilson line operator in the IR, which is basically representative of the word line of massive stable particles. But if it is charged under magnetic force, then it will become a toothed line operators. So then, because in this case, charged object is one-dimensional, any symmetry that can act on this operator or this object can be a one-form symmetry. Now we can generalize. We can think about the surface operator. In the particle physics context, the most familiar object is the cosmic string. So we have a cosmic string at given time, fixed time. There's a one-dimensional string configuration, and it can travel in time and sweeping through a two-dimensional its world sheet. And if there's any symmetry that acts on this object, two-dimensional surface operator, therefore it will be called a two-form symmetry. And in 4 dimensions, there's one more interesting symmetry that we can talk about, which is a three-form symmetry, right? And one familiar example is when there's an autoparameter that changes discretely over very narrow part in space and time, dividing space and time in 2 different regions. Then we can have a volume operator that separating those two, and there can be a symmetry that acts on this three-dimensional object, which will be a three-form symmetry. So this is like, a very easy conceptual way to introduce what higher form symmetries are. But of course, this is not the only generalization that people talk about, and there has been a humongous amount of development. For instance, we are used to talk about a set of symmetries forming a mathematical structure of a group, but recently there has been a mathematical object or symmetries that does not quite fit into this category of being a group, right? So for example, under the name of higher groups, there can be higher form symmetries of a different form degree, and these different form degree symmetry can mix up each other, constructing a particular mathematical structure called the higher group symmetry. And very, very recently, although there has been an indication already in more math or math physics literature, there is even a symmetry that does not come with an inverse operation, therefore called the non-invertible symmetry, which will be one of the central player in my talk today. And there's also what's called the subsystem symmetries that acts only on subsystem rather than the entire space and time, as manifested in a system called the fractal, for example. And there might be much more another generalizations to be explored and discovered in the near future. Just one sentence about how powerful it has been, generalized global symmetry has been in understanding and deepening our understanding of QFT. I mean, it is humongous and beautiful works, and I simply cannot justice all those nice and important work, but certainly it has shown to be extremely, extremely powerful in deepening our understanding of quantum field theory. Now, I'm a particle physicist, and so I had a question. First of all, I found the subject fascinating, and then I had a question whether there can be something useful or meaningful about the generalized global symmetry appearing in particle physics. So the dumbest possible question I could ask was like, are there any generalized global symmetries appearing in 4-dimensional QFTs that are actually relevant for particle physics, right? This is obviously zero-order question that one can ask. Then immediately, as a particle phenomenologist, one can ask whether there can be observable signals, even if it is difficult to actually realize, okay, associated with or due to the presence of those generalized global symmetries. And although in the context of these two questions, I gave a talk at a workshop organized by Harvard back in August this year. There, the basic idea was we take a very familiar local field theories like axion Maxwell theory, and instead of coupling that to a sector of another particle physics sector, which is done every time in particle physics model-building world, but instead we ask, what if we couple that to a sector of a topological quantum field theory? And question number one, whether there is actual generalized global symmetries, the answer is yeah, abundantly. And question number two, whether there are actual observable consequences, and thereby, in principle, we can test such a configuration or situation. And so I talked about that. But today, my goal is not to talk about on this subject. Rather, I raised yet another question back then. And I thought it might be very cool to have answer to the third question, which is like, can generalized global symmetry provide novel or meaningful solutions to any important problems in particle physics? And today, I'm very happy to share with you that yes, in principle, here's at least one example, concrete example, in which there's one important problem, which is to understand the smallness of neutrino mass. And in this example construction, it is really the generalized global symmetry that playing the most important role in answering this important question. Okay, so that's basically my motivation. And here is my outline of my talk. So first, just in case some of you have not had time to thought about it or have a familiarity with the concept, so I will introduce what is a non-invertible symmetry, but I will take pretty practical path rather than formal directions. So I'll just introduce to the level that we can actually speak and talk about it and use it in the game of model building. Once I do that, then I will actually do a quick analysis to show that there is no non-invertible symmetry within the standard model law. Okay, and I will show. And after that, I will extend the standard model with one extra gauge to U1 and show what are the possible non-invertible symmetries. So up to this point, it will be independent of how we might be using this construction. And then I will use the result of the second part of my talk now eventually to construct the theory of neutrino mass. And in particular, I will focus mostly on the Majorana case because it needs slightly less ingredient to combine or to assemble. Although Dirac case is a fascinating and a beautiful features, and to be honest, it doesn't require anything more than that. But just for the sake of time, I will spend most of my time focusing on Majorana case. All right, so that's the plan. Before I move on to the main part, again, if there's any question, feel free to interrupt me.
I just have a very quick comment. I think I understand what you mean, but it's just for 2.1, you say no non-invertible symmetry in standard model.
Yes.
I think that sentence needs a little bit of clarification. So here's yeah, but I know what you mean. I know what you mean. I think more appropriately, you mean no non-trivial non-invertible symmetry.
So sorry. Yeah. So sorry. Good.
And we have to be clear by what it means to have a trivial non-invertible symmetry.
Yeah.
In the standard model, so one kind of quote-unquote trivial non-invertible symmetry is the following. First of all, we have to say in the standard model, what do we do with the Z6? Now, assuming that there is a Z6 one-form symmetry or any one-form symmetry in the standard model, so that's the case in various versions of the standard model, then you can use that one-form symmetry to construct a condensation defect. And the condensation defect is generally non-invertible. But in a way, they are boring because they act trivially on all the local operators. They could have non-trivial operations on the line operators. I think that's what you mean, that in the sense that there could be condensation defects, but there's no other non-trivial non-invertible symmetry in the standard model.
Yes, yeah, I think that's a more precise statement. And of course, also you have shown with your collaborators that within the standard model like the QCD, maybe not like a full fledged 3-generation version of it, but at least once we consider 1-generation version, there's indeed already non-invertible symmetry, which you discuss how to match in the form of a pi 0 gamma gamma coupling.
Right. But in our story, we have to go below the electroweak scale.
Yes. Right.
Anyway, it's a minor comment. Yeah, I know it. Thank you.
Yeah, thanks for the clarification. Any other comments or question? Yes.
So let me just make sure what I get the difference between the trivial a non-trivial, non-invertible symmetry. I'm not sure.
I don't want to commit to a
so maybe once I finish the part 2.1, then maybe that might be the best time we actually talk about the what I mean by non-invertible symmetry, and Shuan can clarify at that point what's the difference. Does that sound okay plan for you, Juven?
Sure. But let me just one sentence say, is a non-invertible symmetry this saying the condensation defects, these are the charge objects, the zero dimension, or was not? What's the dimension of the?
Well, under the non-invertible symmetry, not only the zero-dimensional local operator can be charged, but also two of the line can be charged too. So it's yes or no. I'm probably, yeah, that's what I would say, unless I misunderstood your question.
Because I think Suhong was trying to comment whether there's local operators.
Condensation operators act trivially on all the local operators.
So I guess, Shuang, you meant by condensation operator appearing on the right-hand side of a DD bar fusion
Exactly.
So yeah, those are like higher form symmetry defects. So that acts trivially on the local operators.
No, actually, they are not quite higher form because their codimension is still 1.
Sorry.
But it's funny that they don't act on local operators.
Okay.
Mm-hmm. Yeah.
But the criteria, just because Suhong made a comment, you say about the non-trivial, non-invertible symmetry, you seem to suggest that like an X on some local operator, was in contrast to the condensation defect. That's actually for Suhong, because that's a comment from Suhong.
All right.
Sorry, maybe we should come back to this point when Sungwoo got to section 2.1. Yeah, sorry for the interruption. Please
no, good. This is great. So please do keep doing this. Okay, so with that, let me do my first part of the talk. So again, I'll start with the very simple, but has many interesting features. So simple theory. So here I consider massless QED. So I take possibly NF set of fermions with a negative and positive chiral state charged under gauged U1 gauge group. Okay, so this theory has a global symmetry, U1 symmetry, which I call U1A, which has a Adler-Bell-Jaquiev ABJ anomaly with the gauged U1, which look like this. So under this symmetry, both negative chiral and positive chiral state transform the same way. And again, we have this ABJ anomaly, and which is proportional to, in this case, number of fermions that we introduce, but in principle, anomaly coefficient of NF. Okay, so I mean, hopefully this audience doesn't have any unfamiliarity with if I use these form notations. But I will just switch going back and forth in case someone is more familiar with the indices. So old days, by old days, I mean up until what, 2020 May or something, right? So we say that this means that the U1 axial, classically U1 axial symmetry is broken down to the ZNF by ABJ anomaly effect, right? So that's what we say in old days. But now we say that no, actually, instead of we just saying that this is broken down to that, it actually converts into the combination of what we call usual symmetry, invertible symmetry, and set of, in this case, infinite set of rational non-invertible axial rotations, as beautifully explained in these two papers. Okay. Now, coming back to this question, suppose I do make a U1 axial rotation with the rational angle 2 pi over k. Okay, I'm taking the rotation angle alpha to be 2 pi over k, and this anomaly equation just means that the action gets shifted by this anomaly factor, which is proportional to the alpha, which is again 2 pi over k times anomaly coefficient NF times the Abelian incident factor. Okay, good. Now, of course, by now we are used to use the language of a symmetry defect operator, right? If we have a charged object, in this case, local operator psi of x, we construct a charge operator by integrating the current over the three-dimensional manifold, and the conservation of, for example, this current, which is not in this case, by the way, then ensures that the symmetry defect operator U, which is obtained by exponentiating this charge operator, is topological, which means that if I change the manifold without crossing any charged object, then it would not change, it would not affect the result of correlation function or any physics. By that means. Okay, so in this language, then we note the following. So on a space-time manifold, which is topologically trivial, we on the other hand note that we don't have Abelian instanton. Okay, so now we are in the situation of a two funny situation. In one side, we say that the classical U1 axial symmetry is broken. In fact, if we take NF to be equal to 1, then we would say that U1A is completely broken. On the other hand, I also said that on topological trivial space-time manifold, there is no Abelian instanton. We might say that it's not broken at all, right? So we are in this situation. We don't know the answer in extreme two different situations. As I alluded already, now the correct answer seems to be that this Abelian abigenal anomaly effect is to either break U1A or convert that into not only a set the invertible symmetry of the traditional kind, but also a set of non-invertible symmetry. So let's talk a little bit more about that. So once again, under the U1 axial rotation with the rational angle, action shift by this. Okay, now we are going to modify what we mean by symmetry defect operator. Okay, there are many different directions or different ways of constructing symmetry defect operator, but here I will just take a quick and maybe slightly sloppy direction. So I'm gonna say that I'm gonna modify what I mean by symmetry defect operator. In this case, that acts on the local operator psi of x. Okay, so for that, we recall that in order to define symmetry defect operator, we first define the three-dimensional manifold sigma 3, and on that three manifold, we are gonna write down this is transsimultaneous action at level 1, U1 transsimultaneous action at level 1, right? This is three-dimensional theory that I can write down on the defect word volume. Okay. Now, this theory is known to have, first of all, a Zn one-form global symmetry, and it has a toothed anomaly. And that toothed anomaly can be captured by this anomaly inflow action. Okay. And to be honest, in this case, one of the label P actually needs to be 1, but I'm again slightly a little bit here. So nonetheless, let me say that there is a topological field theory one can write down on this three-dimensional defect, which has one form Zn symmetry, and who has a toothed anomaly, which is labeled by not only the N of one of the labeling of the theory, but also another labeling P that captures, that specifies the toothed anomaly in this form. In this case, here P is the Pontryagin square, and B2 is the two-form background gauge field of this one-form global symmetry. Okay. Now, so I just wrote that theory on the defect. Now, we're going to couple that defect theory to Burke. So here, dA, where dA is the field strength of a Burke U1 gauge field, okay, F. So we're going to couple that in this way. Once we have done that, there's many important and subtle intermediate steps, but roughly speaking, what it does is that it converts or it turns this toothed anomaly into this form. Okay, there's a many more precise way of saying it. For example, this coupling managed to identify, for example, defect one-form symmetry with the Burke one-form magnetic symmetry. Simultaneously, one can say that it managed to gauge this Zn one-form global symmetry of the 3D TQFT through the dynamic gauge field of the Burke dynamic gauge field of dA. But there are many ways of saying it. But for the practical purpose here, this coupling, the coupling between the defect theory and the Burke is more or less turning this toothed anomaly into this form. So once we have done that, then we are on business, right? So let's go back to this section. So we just first did perform the anomalous, rotation with the angle 2 pi over k, and we got this anomaly factor. Now, once I modify what I mean by the symmetry defect operator, including these theories leaving on there, then it also picks up the discontribution from this toothed anomaly. So now, by choosing P over N properly, we have a chance to cancel this against this AB anomaly. So then effectively action might be invariant under that operation under this modified defect operator. So again, this is just the equation that implements what I just said. So starting with the traditional usual sense of a symmetry operation. Now I redefine what I mean by symmetry operation, which is stack of original one together with a three-dimensional TQFT who has non-trivial coupling to the bulk of this form. Once again, I clarify that this particular description is valid only if p equal to 1, but there's a more general story in terms of minimal TQF. But okay, that's a detail. Okay, now this new defect is great because now we have discovered that there's a new set of symmetries we can define. Because in fact, this construction is going through for almost, in this case, for any choice of k here, because I can always choose a proper p over n in such a way that it's equal to nf over k. So in fact, now I have not just a one discrete symmetry to perform, we have an infinite set of discrete rational action rotations we can do. Turns out that this new symmetric defect operator is a non-invertible, meaning it does not come with the inverse operation. So if I have a symmetric transformation with the angle k, and then I can do the same thing with the opposite angle, in this case, oriented reversal version of that, then instead of it being just a 1, so that I know that there's an inverse, it never be actually 1 because it is sum over other, in this case, the condensation defect, or in this case, Zn subgroup of magnetic one-form Burke symmetry defects. Okay, there's details about what these S's are and so on, but nonetheless, the statement is that because of the property of a three-dimensional, principles of a three-dimensional TQFT, there is no situation where for a given dk, one can construct another object in such a way that the fusion of these two is equal to 1. There's no unimodulus partition function of a 3 TQFT. Okay, so in this sense, it is non-invertible. Practically, what matters here is that for any dk, there's no inverse. That's what matters here. Now let's talk about the breaking of a non-invertible. Yes.
Just quickly to recap. Earlier, you used the notation NF. That NF is actually counting the number of Weyl fermions, correct?
Yes.
Because you want to ZNF instead of Z2NF.
Yeah.
And then now you mentioned using you also have a label N and now K. Can you just clarify again the relation between this?
Right. So
K?
NF is the number of fermions which represents the anomaly coefficient, ABJ anomaly coefficient. K is the angle, rational angle I'm taking in this form. Okay. Now, on top of this, so this is the property of the Burke theory, right? In the Burke theory, I can define the fermion contents, and then I can decide, I can determine what kind of transformation I can do. Okay, this is the property of original theory. Now, there are two more parameters which are used to label the symmetric defect operator. So it's about the topological operator contents of the theory. And there are two more, which one is the N, which is associated with the fact that what is the one-form symmetry of the three-dimensional TQFT, that's N. And another label P, which is, in fact, is an extra label of a minimal TQFT, which appears in this Tufte anomaly of a Zn one-form symmetry.
No problem. And N and NF are coprime.
No, here P and N needs to be coprime.
And how about N and NF?
N and NF. The only requirement is that NF over K needs to be equal to P over N, so that it turns into working non-invertible defect operator.
Say again, the only requirement is?
So I just want to make sure that under modified symmetry transformation, action is invariant, which means that this should be canceled by this term, which means that NF over K needs to be equal to P over N. NF and K are properties of Burke theory. P and N are the labels of the non-invertible defect operator. So I'm going to just choose a P over N in such a way that it cancels out this first term, second term.
Okay, thank you.
Yeah. Okay, so we'll get once again this new de facto operator is non-invertible. So now I want to spend some time talking about what one might break this non-invertible symmetry. So so here I want to note that the existence or possibility of constructing non-invertible symmetry de facto operator relies on the existence of Burke warm form magnetic symmetry. Okay, and perhaps the clearest way to see this fact is by deriving this symmetry de facto operator here by actually gauging Zn subgroup of Burke one-form magnetic symmetry. And a paper by Shuang Chao and his collaborator demonstrate explicitly that once you have done that, you can actually construct the same de facto operator. So anyway, here the point number one is that the constructability of the non-invertible symmetry de facto operator relies on the existence of a Burke one-form magnetic symmetry. And in the case of U1 Maxwell theory, we do know that there is one form U1 magnetic symmetry. So we do have that. Now, under this one form magnetic symmetry, of course, the charged object is a toothed line, which again can be thought of as a world line of a monopoles or supermassive, infinitely massive stable monopoles. Now, instead, if there is another UV phase of our theory in such a way that there is actually dynamical monopoles, then it can break this one-form magnetic symmetry. And the simple picture is that given toothed line operator, if there's a dynamical monopoles, what can excite the monopole anti-monopole pair and cut this toothed lines? One can just do it many times, basically get rid of these toothed lines or screen out the toothed lines. And once you don't have a charged object, you don't need to talk about symmetries at all. So there's no symmetry. So one-form magnetic symmetry is broken. Now, because of this link between the one-form magnetic symmetry and non-invertible symmetry, once you break the one-form magnetic symmetry, you manage to also break the non-invertible symmetry as well. Okay. So now let's quickly estimate what might be the size of the non-invertible symmetry breaking effect. Okay. Suppose I have a scale V. Okay, and then the monopole mass goes like a V over G, where G is the gauge coupling constant, and V is the Higgs scale, and the W mass scale goes like a G times V, and this is roughly speaking the cutoff scale from the perspective of IR theory. Now, then the breaking effect, which requires to excite the monopole pair out of the vacuum, goes like e to the minus a monopole action, which can be estimated to be e to the minus a monopole mass times the time that I can borrow energy from the vacuum to excite the monopole pairs. Okay, and from this estimation, one can quickly do that. The monopole mass goes like V over G, and dt, it goes like 1 over lambda. So once you do that, you get roughly speaking e to the minus some number over G squared, which look like, basically e to the minus instanton action. In fact, in the paper by Matt Rees and his collaborators, they have shown that the monopole loop can manage to create the axial potential, which of course by now we understand is related to the violation of non-invertible symmetry. Okay, so here the point is that we can break a non-invertible symmetry by actually breaking the one-form magnetic symmetry. But here the point is that in order to do that, the size of the breaking effect goes like exponentially suppressed to 4. But here, I must say that there's another more mundane or less interesting way of breaking non-invertible symmetry, which goes as follows. Remember, to talk about the non-invertible symmetry, we have to have some classical U1 symmetry. And so far, we assume that the only violation is through the Abelian anomaly effect. But suppose I had a situation where we had a U1 classical symmetry, which is explicitly broken by some random local operators. Okay. If we have that effect, then it can also inject another form of a breaking of a non-invertible symmetry, simply because we started with a classical U1, which was not good symmetry to begin with. Okay, but that's out of control, less interesting. But so therefore here, let me just focus on this particular or more robust breaking, in a sense that if we had the U1 classical symmetry whose only breaking effect is anomalous effect, then the claim is that the breaking of a non-invertible symmetry takes a universal form. And here, I just wanted to show that this estimation can, in fact, be understood as starting from the U1 gauge theory sector. which was responsible for creating, or not responsible for, but related to the existence of a non-invertible symmetry because it had a one-form magnetic symmetry. In the UV, once we embed that into the bigger group, then either we can have a topological monopole, which managed to actually break the two-filter lines, as I described here, or if the embedding is in such a way that we actually do not have a topologically stable monopole, but nonetheless, so long as we have a localizable magnetic charges, even the entire configuration consists of a net magnetic charge 0, that is enough or sufficient to have this effect that we estimate here. Okay, so anyway, here the point is that there seems to be a rather unique way of breaking non-invertible symmetry through this UV magnetic monopole effect or instantaneous effect, and therefore the breaking effect and size is universal, right? Because it goes like exponentially suppress the form. But also, once we have a situation where we do have an observable, we understand that it is coming from the non-invertible symmetry, which I will demonstrate. Then this already indicates that we might be in the good situation where we more or less can understand what might be the universal UV physics, because what can control such an exponentially small breaking effect, we more or less understand what needs to be. It should be a physics of monopole, or more generally, some version of instantaneous effect in the UV. So we have a good anticipation of even deeper UV physics, as I will demonstrate in more detail in what follows.
Question.
Yeah.
So I'm trying to make an analogy. So here the magnetic monopole break the one-form magnetic symmetry, and there are some maybe scale generated, and this is maybe similar to this dimensional transmutation for the scale for like maybe confinement, for example. If you have a confinement deconfinement, then in the modern way of saying there is some one-form symmetry of the line operators. In some scenario is broken, and then there will be some scale generated similar to this exponential, the exponential minus of some G square coupling scale. So is that analogy correct? In some sense, basically.
Okay, I see your point. Right. Their line operators is either Wilson or Tufts are autoparameter for the center symmetry breaking.
Usually that's
Sorry.
Usually Wilson line for the confinement.
Yeah, right. It is a Wilson. Yeah, good. So it is a Wilson line, which is autoparameter for the center symmetry breaking, and thereby you understand confinement versus a deconfinement phase. And I guess you're drawing the analogy that here also exponentially suppressed the scale is involved, right? Compared to the UV cutoff scale. Yes. Here, yeah, I mean, I see some parallel structure here. Although we are going to use this to, well, in fact, not actually to generate the exponentially suppressed scale too. So yeah, maybe some underlying connection, but I haven't thought really much about that deep connection between the two. Interesting point.
Yeah, there usually you require some UV cutoff scale, say M.
Yeah.
And the dimensional transmutation is given by a confinement scale lambda, and that relate to the M by this exponential.
Yeah. Yeah,
I mean, that's one.
In a sense, you will see somewhat similar pattern. Although it's not going to be UV scale times exponential suppression, but some natural size times exponential suppression, as you will see.
Okay, so okay. What's the UV scale you will choose here?
Oh, you will see. I haven't even gone into that discussion yet, so you will see.
Okay, thanks.
Yeah, cool. Okay, so that's my practical introduction, which I spent 40 minutes, surprisingly. So, okay, let me now move on to non-invertible symmetry in the standard model and standard model extended U1. Okay, good. So first of all, no non-trivial non-invertible symmetry in standard model. Okay, so let's first understand the classical symmetry of standard model. Here is the answer. Okay, so there is a U1 of each lepton flavor symmetry times U1 baryon in the quark sector modeled by Z3. How do we understand that, first of all? So in standard model, there are 5 fields, okay? quark doublet and the 2 quark singlet. By singlet doublet, I mean under SU2L. And there's a lepton doublet, there's a lepton singlet. So therefore, one can start with the U3 to the 5th, where Ng is number of flavor. Now, there are Yukawa couplings, and this breaks all the non-Abelian part of the dissymmetries. Okay, just to see a little bit in more detail, in the lepton sector, for example, I can do the field redefinition of lepton doublet L and the singlet E bar using the form of SU3 rotations of their kind to diagonalize. But once you diagonalize this Yukawa, then you completely diagonalize not only Yukawa, but also gauge interaction. So each block diagonal part, you have a free U1 rotations to do. So that's why you see there's a 3 lepton flavor symmetries there. But in the quark sector, you have 2 instead of 1 Yukawa. So you cannot simultaneously diagonalize both by means of a field redefinition. So you do not have individual flavor rotations, but you can have a universal variant number rotations to do. Now, but a Z3 subgroup of this U1 variant global rotation, it turns out to be can be undone by Z3 center rotation of the color group. So it's redundant. That's why we had this modding effect. Okay, that's classical symmetry. In order to figure out the quantum symmetry, then we have to look at the ABJ anomalies. So in the standard model, obviously there are 3 different factors, and color part doesn't do anything because it's completely vector-like. So then we have SU2L ABJ anomaly and the U1 hypercharged ABJ anomalies. And then here I'm listing U1 baryon, which is this, and individual lepton number flavor symmetry here. I also listed U1 lepton number overall, which is the sum of entire lepton flavor quantum numbers. So here, by looking at this, one can check that starting from the 4 different U1s classically, there is 2 ABJ anomalies, but they are parallel to each other, as you see here, right? So the direction of SU2L ABJ anomaly is completely aligned with the U1 hypercharged ABJ anomaly. So there is effectively only 1, constraint. So it reduces the 4 of this down to the 3, which now I can choose, for example, by noting that individual lepton number symmetry has a universal same anomaly coefficient. So if I take the difference of any of the 2, which is free of any ABJ anomalies, so I can combine 2 different combinations. One is LE minus L mu, the other is L mu minus L tau. And then one can also combine baryon with the lepton number by noting that there are different by NC factors, so we can subtract with NC factor there. Okay, so these are 3 quantum symmetry, as you say usually. And now I put invertible because there's there's question of non-invertible. So in order to talk about non-invertible symmetry, let's note that the anomaly coefficient of U1 hypercharge is basically almost the same as SU2, but only differ by universal factor of minus 18, which is due to the field content and charge assignment. So that's the point number 1. So now, do we have a non-invertible symmetry in standard model? So let's note that the non-invertible symmetry is a symmetry broken by U1 instanton, which can be rescued by 3D TQFT effect. However, we also need to note that even on the S4 or topologically trivial spacetime manifold, SU2 group does have instanton. So any symmetry that is broken by SU2 ABJ anomaly are genuinely done, meaning they're really broken. Okay, combining this defect, the question to see whether there's a non-invertible symmetry standard model is that whether there's any symmetry rotation combination of these U1s, which are not affected by SU2L instanton, but only broken by U1 hypercharge instanton, right? Is there any symmetry rotation combination of these which are not affected by SU2L, but only affected by U1 hypercharge? That's the question. The answer is no, because suppose I have done any combination of these U1s with a rational angle like 2 pi over k, but then there's a Abelian instanton factor and there's a SU2 instanton factor, but then anomaly coefficient they are universally connected with a factor of 18. So in order to have a choice of k in such a way that that rotation is not affected or broken by SU2 instanton, then k needs to be either ng times nc or divisor of ng times mc. But one see immediately that any such a choice of K is automatically, free of U1 hypercharge anomaly effect. Okay, so in this way, there is no, it is in this sense that there is no non-invertible symmetry in standard model. Now, there is a schematic way or more intuitive way of understanding this. Okay, in order to have a non-invertible symmetry, we start with the classical global U1 symmetry. Okay, then we say, there is a Abelian instant defect which breaks this classical global U1 down to this subgroup, which we called it now invertible symmetry. And anything that is actually affected by Abelian instanton, we hope to be rescued by 3D TQFT effect, and those are non-invertible symmetry. But what happened in the standard model is that already SU2 instanton breaks way more than what U1 hypercharge does. So this thing labeled by the red or indicated by the red block is a lot of budget. And you can ask whether within this symmetry, because anything outside of that is really gone. So you're not supposed to ask anything about that. So within this red blob, you want to ask whether, do I have a non-invertible symmetry? But this picture manifestly showed that, okay, obviously no, because this is the one that you can ask for, the non-invertible symmetry. Anyway, so that's the sense. I claim that there is no non-invertible symmetry in the standard model. Now, at this point, either Jubei, do you want to raise that question again, or Shu Heng, you want to make a comment again? Either way.
No, I agree with everything you said. Thanks.
Okay. All right. Okay, let's move on. So now, therefore, in order to have a non-trivial, non-invertible symmetry, so now we want to extend the standard model with one extra gauge to one, and the interesting. Yes.
Can I just interrupt? I just wanted to make sure so Shu Heng agrees with everything you said, and I probably will too, but I'm sort of slower than he is. So you're like, it's clear, and your story was to say there's no, that this procedure to produce non-invertible symmetries doesn't work. Are you actually saying something stronger? Like, what, Shu Heng had a sort of universal statement. He was like, well, his idea of non-trivial symmetry would be kind of a non-invertible symmetry which is not connected to an invertible one via some condensation procedure. Is it true that there are none of those at all, or is it just that somehow playing with U1s doesn't produce them?
So I guess one way to tackle that question might be that the way I construct or I talk about the non-invertible symmetry defect, whether that's mathematically equivalent in 4 dimension at least, to another way, perhaps a more general way, that if we have one form global symmetry in 4D, we gauge, for example, in half of the space and time, and then the other we don't. Thereby, by integrating out this gauged part of the theory, we manage to collapse onto this boundary, which is defined to be symmetry defect operator. So, is your question whether the claim?
I think my question is like, what if I could imagine, I don't know, I don't know anything about particle physics, but I could imagine that maybe there was some other thing to use in place of U1, and you analyzed that sort of the U1 case doesn't do this, but maybe there's something else that
good. So, sorry, you mean by means of other non-Abelian gauge factors, for example?
I mean, so like, I guess I would be very convinced if you, for instance, told me some completeness of spectrum statement that just sort of, so Shu Heng gave us this sort of desideratum that said that, well, two symmetries are considered somehow the same if they act the same on the operators of complementary dimension. So like his condensation defects were sort of trivial because they acted trivially on the operators of complementary dimension. And maybe you could convince me that like, there's just, that all symmetries you'd ever need are invertible, even those that don't come from this procedure.
Yeah, okay. I'm not sure if I will have a convincing answer to your question.
Okay.
Meaning whether I do have a mathematical proof that I have checked whether there cannot be in principle any non-invertible symmetry defect. But one thing that I can say is that this claim is true regardless of, I think, global structure of standard model gauge group. In other words, whether there is a modding by Z6 or Z2 or Z3, at least that is robust against that. But having said that, I don't know of answer to your question in a fully mathematically solid way. Maybe others in the audience may have a better answer.
Maybe it's worth saying that you started with, the most general global symmetry that acts non-trivially on local operators in the standard model.
That's true. Yeah.
Right. Maybe that was part of Teo's concern. There aren't other exotic symmetries available.
Okay.
Oh, okay. So if question was about that, then Seth, thanks. I started with the most general global symmetry that can be there at all in standard model.
And just one last question about this, which is that somehow, and maybe I'm just being slow and that you've already done this, but like I could also imagine non-invertible, like that there might be non-invertible symmetries of other form degree. Have you rolled out those two, or did you just roll out non-invertible symmetries of some specific degree?
Yeah, okay, I hear you. I understand the question. I mean, I don't know. There might be such a thing. Whether there is no, maybe it is possible to answer, although it will not affect any local dynamics per se.
Of course,
in a way that we are interested in here. Yeah.
Right. Okay.
But it can be important for defect theory, physics of it. But yeah, I don't know the answer. I don't know. Do any of people in the audience know the answer to the question? No.
I mean, it's a general possibility, but the standard model doesn't contain any such objects. If you wanted to think more generally, sure.
So you're just saying there just can't be anything because there's nothing to act on at all, full stop.
Right. Any other non-invertible symmetry, even if there exists, will not act on the local or particle of the standard model. Thereby, any physics that I will talk about later will be insensitive to those.
Okay, fantastic. Thanks.
Yeah, cool. Thanks for the great question.
Yeah, sorry. Can I ask a quick question real quick?
Yeah, of course.
So the -18 for the baryons and the leptons for like the U1 hypercharge, like the charges are pretty particular. So is it kind of like a surprising thing that they're both -18 coefficients, or is it like a reason behind it? That's not just numerics.
So I said very briefly that this is a basic because of the choice of the field content and the hypercharge assignment of a standard model, and this is universal in any of the diagram because that basically comes from like how many doublets you have, and then you basically count the hypercharge square there. But SU2 case, you only pick up the one because everything is a fundamental representations. So that's a universal difference between two in any of these global symmetries. That's why there's a universal factor. I don't know if that makes sense to you.
Okay. Oh, I guess I'm thinking because it's in a hypercharge case, it's like it kind of looks random, right? A priori, if you look at like what the charge assigns. So I was wondering, like, is -18 like a sum of a bunch of a priori random things that just happen to work out, or is it like it's kind of uniform?
No.
Like
So even in terms of so here, right here, it is like U1 baryon charge and then the field content, meaning whether it's doublet or singlet, 1 or 2 times a Dinkin index of that thing, right? And then you sum up all those over the standard model Fermis. Here, the same charge, but instead of 1 from the Dinkin index of fundamental representations, you have to have a y square, the hypercharge square, right? And but that appears everywhere in any of these U1 symmetries. Thereby, you already know that there should be universal factors differing between these two.
I see. Okay, thank you.
Yeah.
Well, I think the message here, maybe for Leo, is just that B minus L or B minus NCL is some important number.
Yeah.
That's it. Anyway.
Yeah.
Okay. Thanks.
Good. Okay, so now let's get the non-invertible symmetry back. Okay, so we are we're eager to have a non-invertible symmetry. And I hope to be able to show how it can do a fascinating job in real physics. So let's go back to this. So I said that within the standard model, there are just quantum invertible symmetries. Okay, now we want to have extra gauge U1. So now we can gauge any of these factors, provided that those U1 factors is free of also cubic 2-ft anomaly, okay, among all the global symmetry current. And the answer is that with only the standard model field contents, one can gauge any of the lepton flavor symmetry difference. And it is easy to understand why this one is free of a cubic anomaly, because this is manifestly vector-like matter content, because one flavor has a charge 1, the other has -1, but they have the same number of total degrees of freedom, so it's vector-like. Now, one can also gauge, I said also in addition to this, one can also gauge U1 B minus NCL if we also supplement the standard model with a 3 generation of the singlet lepton N. Okay. Now you also understand that because this is competing between quark sector and the lepton sector, differed by factor of NC. But in the quark sector, we have a complete pairing Q U bar D bar. But in the lepton sector, without an N, we only have L E bar, so we are missing 1 degree of freedom. So in order to make a complete vector-like, we just need to supplement another one to balance the number of degrees of freedom. Anyway, here the point is that therefore we can gauge either U1 Li minus Lj in either case, meaning either we do Majorana mass with only the standard model field content, or Dirac neutrino mass including the N, or we can gauge this if we talk about the Dirac case too. But for this talk, I will focus on this gauging of one of the special kind of U1 Li minus Lj, which we take to be U1 L mu minus delta for Pheno regions.
Sorry. What is N without a subscript?
What is N L without subscript? That is the sum over entire lepton number, like Le plus L mu plus Lta.
The N Dirac.
The N
I'm sorry.
in front of Dirac.
I'm sorry. This is the singlet fermion. This is one of the fermion which is uncharged under any of the standard model gauge group.
Oh, sorry. N is a symbol for the Dirac. You don't mean N copies of Dirac.
I'm sorry. This is the extra kind of a field that we add to the standard model.
I see. Okay, I'm sorry. Okay, I see.
Yeah. Sorry for the confusing notation here. And here I'm just giving you the Majorana versus Dirac, because with the only standard model, we have to have a Majorana neutrino mass. With also, singlet N, we can construct a Dirac mass. That's why I wrote that way.
Sorry, in the second case, how many Dirac you ate?
How many Dirac? What do you mean?
Yeah.
Sorry.
How many Dirac fermions do you ate? Just one? Or how many?
So this will make left-handed neutrino of the standard model paired with the N to become a Dirac fermion, or to have a Dirac mass, not Dirac fermion.
Okay. Okay, so you are adding right hand neutrino, right?
I'm just adding 3 Weyl fermions N. I'm adding 3 Weyl fermions N, and it will pair with another 3 Weyl fermion of standard model neutrino to form a Dirac mass. That's what I meant.
So you are
but in general, you can also have a Majorana mass, right? So in the usual seesaw mechanism, people add a Majorana mass.
Yeah. So good. So in fact, I will talk a lot about the Majorana mass. So in fact, in the first path, without supplementing anything with the N, we will have to talk about Majorana mass. And indeed, I will talk about the Majorana mass theory. Yes.
But in the first case, do you also need an additional right-hand neutrino, or you don't need?
No. In this case, if I do not supplement standard model with any of the other matter contents, then the only gaugeable U1 is the lepton number difference, lepton speech number difference. So there are 2 candidates we can do.
Yeah, but usually if we don't add anything, the neutrino cannot have a mass, right? In order to preserve the gauge symmetry, it must be massless.
Good. So I will get to that. So first of all, we will see that it should be massless, and then we'll talk about how to give it a mass by breaking symmetry in an exponentially small manner. That's where we're going.
Let me just recap.
So you're right that if we only gauge, if I just gauge this part at this level, neutrino mass will actually be 0. So Majorana mass will be 0. And then I will explain how we get the exponentially small neutrino mass, starting from there. Okay, good. All right. So
sorry, the second case, the first case, you don't add any right hand vowel fermions for the
yes.
But the second case, the Dirac, you add the 3 right hand vowel fermions. Okay.
Yes. Yes.
And then you in the second case, you do want to implement seesaw mechanism by turning on both Dirac mass and Majorana mass.
No, any other mechanism but our mechanism, right? Otherwise, we are just doing someone else's thing. Yeah, so yeah, right.
Well, but importantly, for good reason, B minus L being gauged prevents the seesaw.
Right. Yeah, it prevents the Majorana mass. I have a slide,
not a choice.
But, yeah, good. Exactly. Good. Thanks, Seth. I have
yeah,
slide,
but a seesaw is some very standard procedure. Why you don't want to use a seesaw in this case? Why you don't just add a Majorana mass?
That's a point for do original research, right?
Right. I mean, so yeah, seesaw is one way to generate the neutrino mass. One way. There, of course, it has its own explanation how you get a small neutrino mass by having ever higher, more massive singlet neutrino sitting there. Very hard to experimentally test, but nonetheless theoretically minimal. Nice. There's a good and pros and cons of those theories. That's just a single, not one theory that can generate neutrino mass. Here, I'm saying that there's another theory where the smallness of neutrino mass is explained by the existence of non-invertible symmetry, which we naively might be missing or confused why it is small, unless we are trying to be able to recognize the existence of non-invertible symmetry and understand how those symmetry might be broken by having monopole instant physics. That's where we are going.
So just last time, so which mass term is turned on? The conventional mass term is turned on.
No, you will see it. Okay, so so far I haven't even talked about neutrino mass term yet, right? I'm just talking what U1 can possibly gauge on top of standard model. That's all I'm saying. And in the 2 or 3 slides, I will write down neutrino mass operator and talk about it. Okay, so great question. Hold on to that. I will get there really soon.
No problem. But since we are here, let me just make one comment. I do envision a different way of giving neutrino mass, even different from symmetry breaking or your generalized global symmetry breaking. It's all different from this. I kind of talked about this when I was in Chicago, but I will comment after you mention yours. Yeah, thanks.
Yeah, good.
Thanks.
Okay, good. Let's move on. So then you see, so we started with the 3 invertible symmetries. We decided to gauge one combination. Then there are 2 effects. One, since I have one extra U1 gauge, then I have to check yet another ABG anomalies. So out of the 2 now U1 symmetries, one combination will have a 0 ABG anomaly with a U extra U1 gauge symmetry. It turns out that combination looks like this: B minus NG times NC times LE. Okay, modulus of discrete effect. And the other combination, any other combination, is anomalous and can come from a non-invertible symmetry. And in particular, we are interested in a direction with the smallest possible ABG anomaly with the U1, this extra gauge symmetry, L mu minus L tau. Why is that? Smaller the ABG anomaly, U1 Abelian ABG anomaly, right? Bigger the breaking by the Abelian instantaneous effect. Therefore, more symmetries to be rescued by the TQFT effect. Thereby, there are more non-invertible symmetries. So we want to have a maximal amount of non-invertible symmetry, and we want to make use of them. Okay, so that's the goal. And turns out this direction, LE minus L mu, turns out to have a smallest anomaly coefficient, ABG anomaly coefficient with this extra gauge symmetry. And we're going to take that as our non-invertible symmetry direction. Okay, let me note one very important fact. There's one unique discrete subgroup of a U1 lepton number, which is a Z3 subgroup, turns out to be also a subgroup of this non-invertible symmetry group. U1 LE minus L mu modulo this gauge redundancy. Okay. Now, in this talk, I'm a little bit abusing the word saying that this is a non-invertible symmetry, even though actually non-invertible symmetry is only the rational part of this U1 rotations. But I'm just abusing word a little bit to say that this is a non-invertible symmetry in case you care about that. Now, okay, eventually with that, let me show neutrino mass operators, because that's
Sorry,
the punchline.
a quick question on the Z3.
Yes.
So as you said, the U1 is not really a group, right? The U1 LE minus L mu is not really a group. That's a non-invertible symmetry. What about the Z3? Is that invertible or non-invertible?
This is a non-invertible symmetry. So you see, there's a bunch of rational angle rotations. Those are non-invertible. I'm saying one of them is a Z3L. It turns out that rotation also coincides with a Z3L subgroup of U1L.
I see. Okay. So this is unlike the in the beginning you talk about NF Dirac fermions in QED. In that case, you have an invertible ZNF subgroup.
That's right. That's right.
But this is different. This Z3 is also non-invertible.
Yes. And the only reason why I mentioned, which I will come back to many times, but this will allow us to keep track of what happened to the non-invertible symmetry once I embed my theory in the UV theory. Okay,
thank you.
So that's why I just mentioned, but I will come back to that many times. Okay, so let's use this to do interesting particle physics. Okay, so I want to generate a small neutrino mass from a non-invertible symmetry breaking. So once again, for the sake of time, I'll only focus on the Majorana case. And I have a slide for the Dirac case, but I wonder if I will have time to get there. But in case some of you are interested, I can talk about it. Now, I talked about radius. There's the same amount of gauge group extended with one extra gauge group, and there's invertible and non-invertible. I mentioned that there's non-trivial discrete subgroup, which is also a discrete subgroup of a U1 lepton. Now, how do I see that the neutrino mass is 0 in this theory? Now, I'm in the phase where U1 L mu minus L top is not broken yet. Okay, so there's unbroken U1 gauge symmetry. Now, in the case of Majorana mass look like this. There's HL with some flavor index ij. It can be electron kind, muon kind, or tau kind, right? Those are the ij index. Now, because of as someone said, because of U1 L mu minus L tau gauge invariance, first of all, the only allowed gauge invariant Majorana mass operator is only 2 of these, right? So LE square and then HL mu and HL tau. These are the only 2 gauge invariant Majorana mass operators. Now, from invertible symmetry, which acts on the lepton as if it is a lepton electron number, we see that the HLE square is forbidden by invertible symmetry. Okay. However, all of these 3 gauge invariant Majorana, all of these 2 gauge invariant Majorana mass operators are forbidden by non-invertible symmetry. And easiest way to see that, for example, is to note that one possible non-invertible symmetry transformation is a Z3 lepton number, and every single one of them carry lepton number 2. So under Z3 rotation, they are not invariant, and thereby they are forbidden by non-invertible symmetries. Okay. Now, so therefore, in order to be able to generate the non-trivial Majorana mass term in the theory, there should be a way to break these symmetries. And I already alluded to the fact that non-invertible symmetry can be broken if there is a dynamical monopole in the UV, or if there is an instant of physics going on in the UV. And that's what I want to talk about. But before that, I want to mention one somewhat important thing before we move on. So we note that I mentioned that there is this invertible symmetry, but somehow, which I will explain how, if this symmetry is broken down to Z 2ng times nc subgroup of it, which when acted on the electron operator, it is basically the same as a Z2 electron number, then there is no selection rules coming from invertible symmetry. Okay, so here I'm just making a statement, which I will show how it is realized in UV theory, that if invertible U1 symmetry of this kind is broken down to this subgroup, again, which is the same as a Z2 electron number, then all the mass operators, Majorana mass operators, are forbidden only from a non-invertible symmetry. Statement number 2, I already said that it is sufficient to use Z3, part of the non-invertible symmetry, to show that it forbids entire neutrino mass operator. Therefore, once we understand the point number 1 and 2, then exponentially small neutrino mass can be generated if this non-invertible symmetry is somehow broken in the UV theory. And that's what I'm going to talk about. And I just wanted to remind you that this exponentially small broken effect of non-invertible symmetry from this slide. Okay, so now let's talk about UV theory that actually achieves the job. So I want to have a UV theory that achieves a non-perturbative breaking of a non-invertible symmetry. And to this end, I want to embed this U1 L mu minus L tau, which was the main and central player in the discussion of a non-invertible symmetry to a bigger group. In this case, SU2H cross U1Z. So here, SU2H is a horizontal symmetry. What I mean by that, so this embedding goes like as follows. First of all, which means I want to have somehow a scalar that breaks SU2H cross U1Z down to some U1 subgroup. So which means I need to have a scalar, which is a fundamental under SU2H, which it looks like this. Okay, so detail doesn't matter too much, but nonetheless, I need to have a scalar that gets a web that spontaneously break SU2H cross U1Z down to the U1 L mu minus L tau. Now we embed mu1 doublet and then tau doublet into a separate SU2H doublet, which we use some notations like that. But nonetheless, there is a SU2H doublet in UV. One of the components is our mu1 doublet and then tau doublet, and you see some other component which I will get to. I do the same thing for the mu1 singlet and tau singlet. We embed it into a separate SU2H doublet like this. Now, we have noticed that there's another component then. What happened to those components? So as I show in next slide, one linear combination of this LE1 and LE2 will turn into electron-lepton doublet, and the other direction will become massive by having a Dirac mass with another singlet field psi L. Same thing happens to the singlets. So SU to L singlets. There's a one linear combination of E1 bar, E2 bar that turns into our electron singlet. And the other combination will become massive by having a Dirac mass with another singlet field psi E bar. So this equation is basically showing what I just said. One linear combination turns into actual electron. The other combination becomes massive. Again, the same thing holds for the singlets, SU2L singlets. One can write down, most general gauge invariant operators. Suppose you have done that. Detail doesn't matter too much. But then let's understand the symmetries and thereby generation of neutrino mass. So classically, this UV theory has this U1L cross U1B modulo discrete effect. How do we see that? First of all, in the quark sector, we haven't done anything. It's the same as the standard model. So there's a U1B, okay? In the lepton sector, we had 6 fermions, okay? 6 fermions. So there are U1 to the 6, but there are a total 6 Yukawa term one can write down, but one can easily convince that there's only 5 independent constraints imposed by these 7 Yukawas. So thereby, there's only one leftover global symmetries, classical symmetries, which we identify as U1 lepton number. And of course, it is convenient to actually combine these two U1 directions in this way. So there's a U1L as just like before, but we combine B and L in such a way that this is free of AB anomaly with the standard model gauge group. Okay, this is convenient basis to use. So then AB anomalies to understand the quantum symmetries as well as anomaly effect. So once again, U1 B minus NC times L is free of all the standard model AB anomaly, but U1L suffers from the AB anomaly under the SU2L, which breaks this down to the Z3. But then we are in the UV phase where we do have extra U1 gauge group, which is SU2H, right? So under SU2H instantaneous effect, U1L is broken down to Z2 lepton number, which I will come back in the next slide. But also under again SU to H instantaneous effect, this U1 B minus NC times L is broken down to this weird looking subgroup, which I will get, which I come back to that later. So let's first focus on the first U1 L part, and now I'll talk about the second part.
Excuse
All
me.
right.
Excuse me. In the previous, in this page, the Lagrangian. Can you explain the notation? Which field is electron? Which is neutrino? So yeah, I'm a little bit confused about this notation.
Good. Thanks. So so that's why I didn't go into too much detail, but thanks for asking the question. And so let me explain. So in standard model, right, there is a lepton doublet. Lepton doublet, by doublet I mean a doublet under SU2L gauge group, the weak gauge group, and therefore it has a two component, and then the upper component is a neutrino, okay, mu1 neutrino, and the lower component is a mu1 actually charged lepton. So therefore charged lepton and the neutrinos are combined in this L field, just like what happens in the standard model. Here too, for example, there's going to be neutrino component as a upper component of SU2L doublet, and there's going to be charged electron component as a downstairs as a bottom component. But then we combine that as a L single field, and then we combine those two to make SU2H doublet.
Oh, I see. So you have additional SU gauge field, so you need to double this.
Yes, that's right. That's right.
I see.
Yeah. Okay. Thanks for the question. Okay. So now let's go back to this question of AB anomalies and understand now generation of neutrino mass eventually. So
sorry.
So yeah.
One question. So when you here taking NG maybe number generation equal to 3, I suppose when you have a breaking, you cannot have an instantaneous breakdown even the fermion parity, which is a Z2 fermion parity Z2 F.
Yeah. Yeah.
And here in the case, when you say breakdown to Z3, do you really mean Z6 that contain fermion parity? When NG is 3.
So are you referring to this part?
For example, yes. Maybe there's additional fermion parity is not broken, right? I just want to, maybe it's a minor comment, but I just want to make sure.
Okay, so the fermion parity -1 to the F
probably not broken.
Yeah, should not be broken. And I wonder if it's redundant with the Z2 center of SU2. I have to check that.
So I think the first order thing to say is just that the fermion parity is a subgroup of B minus L, but not a subgroup of L itself.
That is true. That is true. Right. Okay. Good. So I guess good. So yeah. That is, I guess, free of SU2 AB anomaly.
Okay. And all right. So this resolves. Thanks. No problem. No. But another question is that when you say invertible or non-invertible symmetry protects you from adding some symmetry breaking mass term, right? There are some iterations one by one. You mentioned that, and those are just quadratic mass term. I wonder whether those symmetry also protects adding higher dimensional, higher powers of a fermion operator. Have you?
Yeah. I mean, so good. So yes, I mean, the statement is that it will protect any higher dimensional fermionic operator, so the final statement is that the SU2H instantaneous effect basically breaks the Z3 subgroup of the non-invertible symmetry I talked about completely. So therefore, there won't be a selection coming from that, but the breaking effect should be proportional to the SU2 instantaneous effect. So it will be exponentially suppressed. In other words, the statement is that from an IR theory perspective, any fermionic operator which violates either a non-invertible symmetry will be forbidden. And if they are generated, of course, it is generated just because of the non-perturbative violation of non-invertible symmetry, which means that those Wilks coefficient will have exponential suppression.
Okay.
Does that so okay? Again, in the IR, we know what are the invertible symmetry and non-invertible symmetry. Let's just focus on non-invertible symmetry for a second, right? And that one, if I write down random higher dimensional operator fermions, and if it has non-trivial charge under non-invertible symmetry, right? At leading order, it is forbidden. It should be 0. But then if there's the UV physics that actually breaks this non-invertible symmetry, but that breaking is exponentially suppressed, right? So any operator, therefore, that is charged in the non-invertible symmetry can be there, provided that those risk coefficients will be exponentially suppressed, therefore.
Okay, thanks.
But also there are sets of higher dimensional operator coming from Higgsing effect. But okay, there are details that I can talk about. All right, so but let's go to the punchline because I want to actually at least get to that point. So what happened to each of this? So first of all, I said that the U1L is broken down to Z2 because of the SU to H instantaneous effect, and this is basically I'm showing that. Now under SU to H, we had 4 fundamentals, right? There are 2 L's, 2 E bars, but L's are SU to L doublet, so each of them come with a 2 0 mode. So that's why there are 2 L's of each kind, and then but E bar is SU to L singlet, but it's a doublet on the SU to H. Therefore there's only 1 0 mode. There's a 1 E bar each of kind. But then we had this Yukawa interaction between L's and E bars. We can use that to contract to get the Higgs out of it. So this will generate below the Higgs scale a toothed vertex that looks like this. There's a HL, which is a Majorana mass term operator. There's a instantaneous suppression, but I had to insert the 2 Yukawa, which is tau and then the mu Yukawa that looks like this. Once I expand this and then integrate all the heavy mode, then one landed on this final expression. So there's a mu tau Majorana mass term. There's a mu E squared term, as I talked about. Okay.
Oh, excuse me. So here you still have a U1 gauge field. What do you mean by UV completion? So in the UV, I think U1 the coupling's constant will go to infinite.
So by U1 you mean the U1 L mu minus L tau?
Do you still have a U1 gauge field here? Yeah, maybe I misunderstand.
Yeah, so our theory is that the deepest UV, I had SU to H cross U1Z, and then we spontaneously release onto the U1 L mu minus L tau on top of standard model gauge group.
So U1Z is already included in the standard model or something new?
No, so this part is on top of a standard model. This is outside of the standard model gauge group story.
Yeah, I know, but you still need to introduce this additional U1Z gauge field, right?
True. Yes.
But what do you mean by UV completion if you still have this U1Z?
I see. That's what you mean. Okay. So your question is this is not really UV complete theory. Yeah. In principle, we have to embed into the even
there's a landau pole. So
no, I understand. Yeah, no, that can be done. We can embed it in SU3 or something else. That can be done, and that's easier than the thing that we are struggling here. Yes, thanks. Yeah, now I understood your question.
Okay, thank you.
Yeah. Okay, so now let's understand actually symmetry-wise what really happened.
Is there some non-unified gauge group that include the standard model SU3, SU1, and maybe your U1Z and SU2H?
I mean, we haven't thought about it, but at least one thing that we can definitely have the situation for is that one choice of a mixing angle corresponds to the case where this is embedded into SU3, for example. So then one can further think that there's an SU to left, U1 hypercharge, SU3. One can maybe SU to left cross U1 hypercharge can embed into another SU3. So you have SU3, right? SU3 cross SU3 or something like that.
That's a nice one.
Yeah, one can play cut K as usual. Okay, so we can go there, but let's not for now. Okay, so let's understand what just happened. So again, once SU2 instanton breaks U1L down to the Z2, but then I mentioned that one of the important non-invertible symmetry is a Z3. Okay, And but then again, UV instanton leaves out only Z2 part. And I said one or two times, but let me say that again. Z3 lepton is the only discrete subgroup of a U1 lepton, which is also non-invertible symmetry. So this uniqueness shows, therefore, that the instanton breaks this completely. So therefore, this theory breaks the non-invertible symmetry completely, and therefore now that's why we had this exponentially suppressed violation of a non-invertible symmetry, and hence we have this mass operators. But then you may recall that L mu E squared is also protected by the invertible symmetry, right? And so what happened to that? So for that, let me go back to this slide that I talked about, right? There's an HLE square operator is also protected by the invertible symmetry. But I also said that once this symmetry is broken down to the Z2 Ng times Nc, which is effectively the same as the Z2 electron number, then this operator is allowed. So in the context of this, then one can show that SU2H instanton breaks this another U1 symmetry, this symmetry in the UV down to this. And one can show that below the Higgs scale, this is equivalent to this Z2 times Ng times Nc modulo gauge redundancy. So indeed, this instance so leaves out only the ones that, just so that there is no selection rule imposed from invertible symmetry either. Okay, so this is extremely economical in the sense that a single instanton managed to break both invertible and non-invertible symmetry, therefore leave the entire selection rules imposed by both of the symmetries. So as a result, single instanton kills all of that, and we ended up getting this Majorana neutrino mass below the Higgs scale. Now, I want to quickly mention two interesting properties. For one may wonder, looks like we only generating mu tau component and E tau component. I don't know if there's a phenomenologist in this audience, but a few people might say, no, we have observed the many other components through the neutrino oscillation. How does that is it consistent with the observed neutrino oscillation phenomena? So I think it's a very interesting and important to actually compute within our theory the exact structure of the texture, meaning the other component in the neutrino mass operator or mass matrix. But here, I just want to make a reasonable argument that why we should expect to generate other component as well. So below the Higgs scale, where SU2H cross the U1Z is broken down to the U1 L mu minus L tau, obviously in real world, we have to break this extra U1 gauge here, because otherwise we have another message gauge goes out. We haven't seen that. So we have to break it, which means that we have to have another scalar has a charge, non-trivial charge under this extra gauge group, supposedly at charge 1. Then the UV phase, once the instant physics is done, then generically it will generate along the RG flow another operators, which now involves the extra Higgs field that needs to break this extra U1 gauge field of this kind. So there's the details, but the point is that all these operators naively are charged under invertible as well as the non-invertible symmetries. And now I can write down these operators. Of course, when I can do that, I'm saying it is consistent with the U1 L mu minus L tau gauge invariance. But since these are all charged under invertible, non-invertible symmetries, the fact that I can write down this also means that it also needs to be proportional to the breaking effect too. So therefore, there's universal instanton factor sitting there. That's property number one. Property number two, one very unique thing about the non-invertible symmetry in the context of particle physics we have found is the following. Naively, in a lot of cases in particle physics model building, if you have some new physics and there's a very high physics scale, often it's very hard to say what one should expect and when one should expect to see another yet UV physics. But here, non-invertible physics seems to provide a good anticipation of the form and even the scale of the new physics. Okay, so here the comment is the following. So what just happened was that there was a UV physics with this gauge group, and there's a Higgs scale broken down to that, right? Now, in the UV, there is an instanton and the two of the vertex. We have generated the Majorana neutrino mass as follows. So let me just look at this. So it looks like this with
Excuse me, yeah, I'm still a little bit confused about your notation. So in the previous formula, can you go back in this formula? So this one. So nu and tau is the usual neutrino field.
Yes, this is our neutrino field. Yes.
So E is the electron field.
E, you mean the
Nu
E?
Nu
Nu is the
E.
electron flavored neutrino field.
I see. But this direct neutrino mass term will also break the standard gauge group symmetry, right? Like SU2 and U1.
No, so good. So you mean there should be a spontaneous breaking of SU2L if that's what you meant.
Right.
So good. Then, you're right. So let me actually go back. So in the deep UV, because of the this instanton, what we generate is a manifest SU2L invariant SU2L cross U1 hypercharge invariant operator. Right? And then I can expand and turn this into actually a mass term once electric symmetry is spontaneously broken. That's why I have insertion of electric van B square here. And only then, all of a sudden, I can see individual neutrino field appearing there. Otherwise, it should be housed into a lepton doublet field.
So what's the H here? Do you still need a Higgs field, or you don't need a Higgs field to break
this? This is our Higgs. This is our Higgs.
That's the usual Higgs observed in the experiment. Okay.
That's right. This is the usual Higgs.
I see.
Yes. So after this physics, what it generates is the operator, not just the mass yet. This is the manifest SU2L cross U1 hypercharge invariant mass operator. Okay, this is the operator, but not mass term yet. But only after electrosymmetry breaking that all of a sudden this term includes now what I can call a mass term for the neutrinos.
Yeah, but this action before you condense the Higgs particle, it's not renormalizable, right?
It is not renormalizable. This is dimension 5 operator, and Majorana neutrino mass is necessarily dimension 5 or higher.
Yeah, but in the seesaw mechanism, I think it can just write down this dimension 4 operator, right?
No, it is also dimension 5 operator. So there, you have to integrate the singlet n. I don't know if you see the cursor. And there's Higgs L, Higgs L. By integrating n, a heavy singlet n, you also generate basically the same operator divided by the mass of the singlet mn. There,
right, but before you apply, before you integrate it out, I think all the terms are just renormalizable.
Of course, but there is no Majorana mass operator yet. It has not generated yet. Only after you integrate out the heavy singlet, you eventually get the Majorana mass operator, which is dimension 5 Weinberg operator.
Yeah, but there I think at the UV it's renormalizable. But here, if you add this bare mass term at the UV, it's still renormalizable.
No. So I started with the renormalizable theory, and this is generated, not put by hand, by the non-perturbative instantaneous effect. This is two the vertex of this instantaneous effect.
Oh, I see. Yeah, maybe I missed the understanding this part.
Oh, I'm sorry. So probably I went too fast.
Okay.
Okay. Hopefully that clarified something for you. Okay. Okay, so I talked about texture. So what about this? So in the UV, we said again, because of this instantaneous effect, it generates this dimension 5 operator, which is exponentially suppressed. So we have this estimation of the neutrino mass, which is proportional to, importantly, it determines 2 pi over SU2H gauge coupling evaluated at the VAF scale, V5, right? Now, SU2H cross U1 Z is broken down to unbroken U1. So there's a mixing angle between SU2H gauge coupling and then L mu minus L tau gauge coupling, which is parameterized by the sine theta H. Now, suppose we have discovered, a massive U1 L mu minus L tau gauge boson, because this needs to be Higgs eventually. Suppose I had discovered that and called the gauge boson associated with the U1 L mu minus L tau to be Z prime. And then suppose we also have measured experimentally the gauge coupling at that scale. Now I can connect this discovery to this particular mechanism of a neutrino mass generation by RJ evolution, right? So I can either run up, run down to match between this measurement to the gauge coupling at this scale, which is now related to this Tooth vertex. So once we use these RG equations to plug in, therefore matching between these two quantities, one arrived the following expression, for example. So once again, we know mu, we measured it. We know the mu mass, we know tau mass. And so suppose I said that we discovered the Z prime, say at TV, we measure the gauge coupling. And then this expression connects those known observable quantities to what might be the new physics scale where the instant of physics happened and generated neutrino mass via this violation of non-invertible symmetry. Of course, in this expression, there is a one degeneracy, which is this mixing angle sine theta h. So in principle, it does not point to the unique scale even after you make some discoveries at, say, Z prime mass scale. So this shows one of those dependence, but for the sake of time, let me just move on to the next slide. However, we discovered in the case of Dirac mass, which unfortunately I didn't have time to talk about, there's a unique relationship. Okay, so it's pretty beautiful. So if we discover Z prime, if we discover gauge coupling, and if we understand the existence of non-invertible symmetry that protects the neutrino mass, and then once we are there, we immediately almost know that what scale we should expect yet another UV physics that was responsible for the generation of neutrino mass, or more precisely, violation of non-invertible symmetry that protects the neutrino mass operator. Okay, so okay, with that, let me stop here. And I'm sorry for running over time.
No, you have time. You can take your time. Don't worry.
Oh,
you really take your.
Oh, really? Okay,
let me ask a question.
Yeah,
sorry.
let me stop
ask
for now in case there are questions from the audience.
Okay. Yeah, let me ask a question. I guess you shouldn't just soundly finish. Can you just remind us what's the theta L and theta H again? This angle, I didn't get it the first time you mentioned. Sorry.
Oh, okay. Yes. So good. Yeah, probably I was rushing. So because there is a spontaneous breaking of a gauge symmetry, SU2 cross U1 down to the U1, right? So then this U1 is a linear combination of W3 from SU2 and then Z gauge boson. So therefore, the gauge coupling of this unbroken U1 is, in a sense, a linear combination of the gauge coupling of this and that, which can be rephrased in terms of gauge coupling of unbroken 1 is the gauge coupling of SU2 times the mixing angle.
Okay.
Which is a function of gauge coupling of these two.
No problem. This is theta H.
Yeah, that's what I call the sine theta H.
How about theta L?
Theta L.
Yeah.
Where did I mention theta L?
When you write some Lagrangian between Perry and Sung.
Oh wow, you captured that. Okay, so yeah, okay, here.
Yes.
Yes. So good. So yeah, good that you captured it. Or so good. What happened was the following. I said that here. So I said that in order to embed the field, there are two SU2H partners, right? For the one for the mu1 doublet, another for the tau doublet, right? And then one linear combination of that turns into our electron. The other combination becomes heavy electron. So the mixing angle that captures this relationship is the theta L. Now, remember that, therefore, both LE1 has an LE component. Also, LE2 has an LE component, which is proportional to either cosine of theta L or sine of theta L. Now, what happened was that in the neutrino mass operator, this one includes a contribution that looks like LE1 times LE2. So LE1 has our electron, which is proportional to, for example, sine theta L. LE2 has our electron component, which is proportional to cosine theta L. That's why you see this sine 2 theta L.
Okay, thanks.
Yeah.
Excuse me. So for this new gauge field, SU2 gauge field, it only couples to lepton, right? Not to quark.
Correct. Yes.
But does it also have this anomaly cancellation? In the usual SU2 chiral gauge field, we require to couple both to quark and lepton to have this anomaly cancellation, right?
So okay, good. So basically, you're questioning whether
so here this new gauge field is also a chiral gauge field, right? It's only coupled to left-hand particle, not right-hand particles.
Right, sure, but then yeah, okay. So basically, you're questioning about the mixed gauge anomaly because SU2 alone doesn't have the perturbative anomaly. So you're worrying about the U1 SU2 square mixed gauge anomaly, or?
Right. Yeah.
So, but that you see, this is U1 under U1Z, it's a manifestly vector-like, as we set it up. So that mixed anomaly is not there.
I see. But how about this? Sorry. How about this non-derivative anomaly? I remember there maybe also
non-perturbative anomaly. Good. So that we have even number of fundamentals. So it's also free of a Witten anomaly.
I see. Okay.
I think maybe Zhenchen already asked, but let me just double check with you. So is phi here the Higgs field?
Yeah, this is the field, scalar field that Higgs is this down to the U1 broken.
This is different from the standard model Higgs, so the standard model Higgs.
Right. This is on top of, or external to the they're on top of standard model gauge group story.
Other Higgs, other scalar field.
This is another scalar field.
The scalar field, no problem. But earlier, I think when Zhenchen was asking something, I think you used the Higgs scalar field to the standard model Higgs.
Yeah, here.
Yeah. Right. So just remind me the relation between the two.
Right.
One is to break down SU2H.
Yeah.
And however, the standard model Higgs still can give rise to some mass to the neutrino.
Good. So let me clarify that because that's important. So the full gauge group is a standard model gauge group, right? SU3 cross SU2 left cross U1 hypercharge, and SU2H cross U1Z. So that's the starting point. Now, sorry, there is a heavy scalar, like the supermassive scalar, that spontaneously break this gauge group down to the unbroken U1. So below the valve of this capital phi, we will be in the phase of a standard model gauge group times U1 L mu minus L tau. Okay. Now, but in the UV, before we reach the spontaneous breaking scale of the phi, then because of this ABJ anomaly, then those anomaly generates the two of the vertex of the fermion zero mode. But then since we had this gauge invariant Yukawa interactions, then one of the derived version of two of the vertex from the fundamental vertex is this one, because I had two L's, and one E bar. I can contract a one E bar with the L to get the Higgs out of it. I can do the same thing to get another Higgs out of it using these two low perturbative interactions. So as a result of that, this effectively generates the HL. But if you keep track of correctly momentum flow, in fact, this is actually H tilde L, which is the correct operator for the Majorana mass. And here, this is actually standard model Higgs. So this H appearing in the theory, UV theory, is our standard model Higgs. Okay, and so that was the story.
What's the difference between H tilde and H?
Oh, so yeah, so H is a doublet, right? There is a phi 0, phi minus. H tilde is basically flipping order and then turning to that way. So in other words, basically, okay. Operationally, the meaning of that is epsilon 2 times I sigma 2 times H star. So it's conjugation operation. So
I know that. Yeah, I know that.
Yeah.
That's
yeah. Right.
Okay, thank you. Yeah, you can go on where you skip the many things. I guess you still have some other. You have some other things you want to mention, but you quickly skipped it. I think you can just still go through it.
Okay. No, so I just prepared a couple of slides for the Dirac because it's interesting, but it needs some extra ingredient. But I mean, I can mention it if people are interested in, or if people have more questions, I'm happy to take. Either way is fine.
I think how about you mention it and people will still ask, I guess.
Right. Yeah. Okay. Good. So yeah. So yeah, in the case of Dirac, the intermediate scale physics is basically almost the same. So here, in addition to the standard amount of matter content, we add three generation of a singlet N field. This comes with the electron flavored N, muon flavored N, and tau flavored N. Then once we decide to gauge U1 L mu minus L tau, one can run the same argument for the symmetries. So we start with the U1 Li, three of them, U1 Ni, three of them, and there's a U1 B. But one can check which of them are free of all the A Bijet anomalies. And this is a choice for the A Bijet anomaly free part. So this is invertible symmetries. And then another direction, therefore, can be invertible symmetry. In particular, yeah, so one can choose this to be that. I can explain where they come from compared to that, but okay, maybe that's too much. So there's the one direction one can choose to be non-invertible symmetric direction. So now we are interested in having a Dirac mass operator because there's a standard amount of neutrino, there's a singlet. We can write down this. Again, similar way, we can check that these symmetries protects this operator. Then to break those non-invertible symmetry in particular, we can embed now this into SU2-3 horizontal symmetry. So now it's pretty elegant actually, because all three generations of a lepton doublet, Le mu tau, are embedded into a 3-column one fundamental representation of SU3H. I can do the same thing with the singlets, E bar, mu bar, tau bar. We can just embed into the single fundamental, anti-fundamental under SU3H. And then we had also 3 generations of N. We just embed into the single anti-fundamental under SU3H. So that's all the matter contents. And one can do the analysis of U1 symmetries or global symmetries in the UV. But the point is that here there's basically one Gauss invariant operator one can write down. There's a standard model Higgs, lepton doublet, and then lepton singlet. This is literally lepton Yukawa, and then the natural size might be the largest one in the standard model, which is the tau Yukawa. We can write down. So skipping through some of the detail about the global symmetry analysis, now the physics is the following. Now in the UV, so we have 3 either fundamental or anti-fundamental under SU3H. And here there is U1 L tilde, where L tilde is a lepton number under which only the standard model leptons are charged. And on top of that, there's also U1 N global symmetry, which is basically capturing the N number here, single N number here. So then one can check that these are anomalous under the SU3H instanton. So one can now construct the 2 of the vertex from SU3 instanton. And once again, there are basically 3 bar. So there's only 1 zero mode. But remember that the L is SU2L doublet, so there are two zero modes. So there are 2 L's and then 1 E bar, and then 1 N. Again, using this unique perturbative operator, we can write down, we can contract 1 L with a 1 E bar. So once you do that, so we ended up getting HLN, which is precisely the Dirac mass operator for the neutrino. And in fact, we can understand symmetry-wise why this is happening, because this instantaneous fact or ABJ anomaly breaks precisely U1L tilde and U1L by 1 units. That's why we are allowed to have this operator, because we are violated only by 1 unit. And in fact, this for B's, for example, Majorana mass operator. And then one can estimate the size of the neutrino mass from this operator by expanding the fields there. Basically, there's a y tau, and then Higgs fab, that's m tau. There is an instanton factor right here. And then I can, again, match between V phi scale to the coupling, say, at the scale where IR U1 L mu minus L tau is spontaneously broken, which is Z prime scale, through this RG equation. And I can just massage this equation a little bit, looks better like this. Then I can just, rewrite this equation that connects the M nu with the B phi and then other measure of quantity in terms of B of phi. So this equation is exactly the one that I showed earlier, that M nu is known, M tau is known. So once we discover Z prime, say TV scale, and measure its phase coupling, at that moment, once we understand there's a Dirac mass for the neutrino, and theoretically we understand there's a non-invertible symmetry, then we can anticipate the next scale for the new discovery, or at least new physics, in case it's too high to be discovered. So that was roughly the quick summary of Dirac mass case. Anyway, that was the rest of the slide I had. Yeah.
Okay, thank you very much.
Yeah, thank you.
Thank you so much.
Thanks.
Thanks again for the nice talk.
Thanks. All right. Thank you very much.
See, will any audience have a comments, questions, please?
Excuse me. Yeah, actually, I have one more question. So in your story, the number of generations is important or not? If you have 3 generations, 4 generations, you have different results.
No, overall, yeah, it is important, and it is important, even though. So, for example, one thing that we try to be careful is we really try to have a realistic actual standard model, including all the structure of a 3 generation, all the Yukawa coupling, non-trivial textures, and whatnot. And within that real standard model, we try to understand the general story about the symmetries, including non-invertible symmetry, and so on. So yeah, so the generation was important. If your question is like, if I take ng equal to 4, what happens? If that is your question, theoretically, one can go through the analysis that I have done here. Phenomenologically, that is more or less ruled out. So there's no point of actually taking other values than ng equal to 3. The reason why we kept equations with a general thing is to manifest the symmetry structures and relationship among the different U1s. Okay, it's not random 3, but it's 3 is because it's regeneration and so on. So that's why we kept the ng as a notation rather than put 3 there, because otherwise we will forget the intrinsic relationship among other symmetries. So that's why.
So I remember you also mentioned this U1 L mu minus L tau should be regarded as a certain kind of discrete symmetry, right? Some discrete subgroup.
Yeah, good. So the context where I mentioned was when we try to understand. So below the B phi, where this type of physics happens, right? We understood the non-invertible symmetry. We understood the invertible symmetry, how neutrino mass operators are protected. But then once we switch back to the UV physics, of course, the size of the symmetry, a form of the symmetry look different than the kind of symmetry we see in below the B phi. So we wanted to have a matching between UV and IR or intermediate scale. And this Z3L, for example, and this discrete symmetry subgroup are the ones that actually provide us the explicit contact or connection between UV and IR. And that's how we can keep track of the fate of the symmetries we saw in the intermediate scale versus the UV physics. So in this context, for example, I said that the J3 lepton symmetry is one particular non-invertible symmetry, which is a subgroup of a U1 L mu minus L tau, which is also, in a sense, shown up in the language of a U1 lepton number in the UV, which is now broken down to Z2L. So we can actually see from this relationship what happened to the non-invertible symmetry. Of course, the answer being it is completely broken by the institute effect.
I see. So here, but yeah, I'm still a little bit confused. So here, this Z3L belong to this U1. It's also a gauge symmetry, right? Or it's just a global?
Oh, I'm sorry. Now I see why. Okay, it was supposed to be LE minus L mu. That was the non-invertible global symmetry. I'm very sorry for that. I'm very sorry for that. So there was a typo there. This should be LE minus L mu actually.
Oh, so for the gauge symmetry, it's always U1.
Yes, gauge symmetry is always just the U1 L mu minus L tau. Sorry, this is a bad typo. Yeah. This caused to be confusion. Yeah. Thanks for catching it. Yes.
Can I try to understand maybe rephrase your result? Am I correct to maybe rephrase in a way saying that you still give a neutrino some Majorana mass or Dirac mass, but they explain that how the mass can be small in a more natural way?
Yeah, that's right.
Breaking some non-invertible or generalized symmetry.
Right. So yeah, so good. So let me summarize in 2 minutes what just happened, right? So
to the more conventional, maybe seesaw mechanism and others way of giving small mass to the lepton neutrino. I guess that's a part. Maybe we can also understand, is there some relation or it's actually still very different? Yeah, thanks.
Right. Good. So first of all, before making a comparison, what we have achieved is that there is a setup where neutrino mass, either Majorana or Dirac, are protected by non-invertible symmetry. So if we don't know how to recognize non-invertible symmetry, we will be simply confused, right? Because it looks like there is an operator with a zero coefficient, and looks like we cannot find any symmetry argument unless we actively looking for new generalized version of symmetry. In this case, non-invertible symmetry. That's fact number one. Fact number two, the way non-invertible symmetry can be broken is pretty unique. It's not like there are a million different ways of doing it. In fact, there's a universal way of doing it, which is only through the monopole or instantaneous effect, and so necessarily exponentially suppressed. That's fact number two. Fact number three. Now, once we are in a situation where we understood that the neutrino mass is indeed protected by non-invertible symmetry, and it is actually coming from the violation of non-invertible symmetry, then non-invertible symmetry provide us to make a very good anticipation of a form of and the scale of the new physics that actually achieves that. This is a very unique, I think, to the non-invertible symmetry. Many other physics doesn't come with that unique information, because the non-invertible symmetry is an ideal remnant of UV instant of physics. In that sense, it provides us to make a good prediction about yet another new physics scale and the form of it. So that's kind of summary of what just happened. Compares to the seesaw, nothing can compare to the seesaw because it's so simple that what can you say? Okay, it's a seesaw. But here, nevertheless, a seesaw, the smallness is explained in the power law fashion. right? In order to have a smaller, you have to raise this guy more and more. So it's a parabolic fashion. On the other hand, in our construction, it's precisely a combination of a parabolic separation and exponential separation. So maybe new physics can be much closer than what CISO, for example, mechanism would indicate, right? It's not going to be 10 to 12, 14 GeV. Maybe it's much closer because exponential separation actually helps a lot. But also it's just simply very, very different, right? It's very, very different. In CISO case, you have to add explicit lepton number violation by hand, right? But here, we just everything is done by dynamic break, non-perturbative violation. So I mean, yeah. So it's just different, I guess.
It helps.
Yeah.
Very good. Thanks.
Yeah. Thank you. Okay.
Any other question, comments? Okay, if not, we should thank Sungwoo again. Thank you.
Thank you, Ivan, and I hope to see you soon somewhere in the world, in person. And Seth, I will talk to you sometime soon.
Yeah, that was great.
Yeah, thank you. Thanks for coming.
什么是你的